Greetings, everyone. My name is Norm Jones, and on behalf of my co-authors Sergio Barbosa, Sarva Pulla, Gus Williams, Dan Ames, and Bako Mamane, I am very excited to tell you about some research we've been doing as part of our NASA Severe project in West Africa. And the work I'm going to talk about today is related to regional subsetting of GRACE-derived groundwater storage estimates and how we're using that to assist our partners at our West Africa hub. And the objective of our Severe project is to assist our water resource managers and decision makers and stakeholders in the countries in our West Africa hub, specifically in southern Niger, to characterize their groundwater resources. Groundwater is a critical resource for economic development, and also this region historically suffers from crippling droughts that appear every few years. And in order to make them more resilient against these droughts, there's a really strong interest in developing groundwater infrastructures. In order to do that, they have to have a better scientific understanding of the groundwater resources they have, how much is available for development, how that's changing over time. So with those broad objectives, we have been working on some specific deliverables, and the one I'm going to be talking about today is a GRACE regional groundwater subsetting tool that assesses long-term changes in groundwater storage in the region. I'm going to assume most of you are very familiar with the GRACE and the GRACE follow-on missions, but in a nutshell, two satellites that orbit the Earth in a synchronous fashion, and the distance between the satellites varies slightly as they're tugged apart due to variations in mass on the Earth's on the Earth. And by looking at those changes, and as this rotates, these satellites circle the globe in a systematic way each month or so, we can get a map of the gravitational field across the Earth, and then if we compare changes on how that from one pass to the next, we can come up with a change in the gravitational field, which is when we account for things like seismic shifts, we can assume that the primary driver of those changes is the change in water storage, in snow, in surface water, soil moisture, and groundwater. And so this is, in order to explore and analyze the GRACE data, we have developed a web application using a software toolkit that we've developed here called Tethys Platform. And this is our GRACE groundwater subsetting tool, and there are a number of things that we can analyze with this that I'll be talking about today. But what you're looking at here is a map of the globe, and this is a raster that shows total water storage anomaly. So this is the total water storage change that we've inferred from the GRACE gravitational signal. And this, one of the features of this application is you can drop a pin. If you look up around if you my cursor here, the Central Valley roughly in California, you can drop a pin and then it shows the change in total water storage measured in centimeters of thickness over a grid cell. And this app allows us to animate that raster. If I were live, I could click on the play button and you'd see that change over time, and then the red line here would then move to show you at which frame you're looking at, or what point in time the raster is displaying as part of the animation. And so that's extremely valuable, but what we really want is groundwater. And so to get a groundwater anomaly, we have to do some calculations, and this is a relatively standardized process at this point. We're certainly not the ones to invent this. But what we do is we take the GRACE total water storage anomaly, which we've labeled here as TWSA, and then we subtract from that three things shown there in parentheses: SWE, CAN, and SM. This represents a set of volumetric storage anomaly components which we get from the GLDAS model, the Global Land Data Assimilation System. And from that, we can, and this uses a number of Earth observations and in situ data as input. And if we look at it over the same time frame as the GRACE missions, 2002 to 2000, or to the current time, we can pull out the snow water equivalent anomaly, the canopy storage anomaly, and the soil moisture anomaly. And those together represent the bulk of the surface water storage, the non-groundwater component of the total water storage anomaly. So if we subtract those from the total water storage anomaly, what we're left with is an estimate of the groundwater storage anomaly. And so now it just so happens that the GLDAS actually consists of three embedded land surface models. And those include CLSM, NOAA, and VIC. And each of these models does the same kind of calculation, but it uses a little bit different technique and assumptions. And by the way, what we use to do this groundwater anomaly calculation is the mean of the values from each of these three models. So here where I say snow water equivalent, we're using the mean value, but we also keep track of what that spread is in the prediction of snow water equivalent. I'll come back to that. And you'll also notice that each of these models calculates soil moisture zone a little bit differently. And this table kind of shows, you know, what part of the soil moisture output that we pull in for each of these. And then there's also an issue of grid resolutions. The GRACE total water storage anomaly is at 0.5 by 0.5 degree. The GLDAS, VIC, and CLSM models, the snow water equivalent canopy storage and soil moisture are at 1 by 1 degree. NOAA model is actually much finer resolution, is 0.25 by 0.25 degree. But we have to do our raster algebra with all of these together, and so what we've done is we've kind of scaled them to the 1 degree by 1 degree, which gives you a little bit coarse grid, but a little bit safer in terms of how you're scaling things. And so we end up with a groundwater anomaly at 1 by 1 degree. We're working on a new version now where we'll just use the NOAA model and get a 0.25 by 0.25 degree groundwater anomaly. But in general, we want to have input from all three of these models, so we end up with a 1 degree by 1 degree groundwater storage output. And then since we have inputs from all three, we know what the spread is, the uncertainty in each of these components, and NASA publishes an uncertainty on a cell-by-cell basis over time for the total water storage anomaly. And by looking at the differences in the calculations between the NOAA, VIC, and CLSM models for each of the three components, we can come up with an uncertainty. And using this equation, this gives us then an uncertainty for the groundwater storage anomaly. And then when we display that on our app, we can then put on a band around our curve, which is the mean, that shows you the spread. So the thicker that band, the greater uncertainty at that particular point in time. And it changes with time. And some points in time, they're mostly in agreement, and other points in time, there's a little bit more spread. And so we put that into our application, but we also add another really important feature. Our algorithm includes a regional subsetting analysis option where you input a shapefile, and it then will, first of all, it'll clip the raster, the global raster, to your region so that you can animate that by itself. But it also takes the aggregate change in water over that region and calculates a time series for each of those water components: total water storage, surface snow water equivalent, etc., down to groundwater, and we get a regional storage anomaly curve which we can display. Now, we are using this, applying this right now to an analysis of groundwater storage changes in southern Niger. And we're targeting two different regions. We have some aquifers in the Illumidan Basin that we're looking at, and then some aquifers in the Chad Basin. And we're feeding this into our system. And this is the groundwater storage anomaly for the Illumidan and Chad Basins. And what's interesting is from 2002 to about 2011, it's fairly flat. But then over the last 10 years, there's been this steady upward climb in groundwater storage. And we're not, this is consistent with what others have found in other regions of West Africa. But this is new data because it's specifically for those aquifers and basins I showed. And it shows we're getting about 1 centimeter per year accumulation in the Illumidan Basin and about 0.5 centimeter per year in the Chad Basin. Another thing that our regional subsetting tool does is if you take 2002 as time 0, it then calculates the net change in groundwater storage from that time. So this is a cumulative groundwater storage change. And we also convert that to millions of cubic meters. So we multiply the centimeters of depth that we get from our analysis by the area of the aquifers or the regions being analyzed, and that allows us to come up with this curve, which is really helpful for water managers. This is a volumetric illustration of how the water storage is changing. And again, you'll see for the first 10 years or so, it's fairly flat, but then there's this steady upward climb and a very significant accumulation of groundwater in the Illumidan Basin, and also some accumulation in the Chad Basin as well, which is really interesting. Another thing we're working on is using this information to do recharge estimates. If you go back to the groundwater storage anomaly, there's a seasonal component to that where it goes down and up. And if you look at those individually, and you look at the trough versus the peak, so in the first part, we're in the dry season when the groundwater is declining, and then the wet season when it's recharging. And we can come up with a recharge estimate. And this is still ongoing, but we're excited about the potential for this. And thus far, the recharge estimates we found are very consistent with what's been found in other studies. And we're excited to publish that soon. Everything that I've shown you is available on the internet. There's 2 different portals where you can access these applications and play with them. We also have the analysis code associated with available in a Jupyter Notebook format. So totally open source. And we recently published a journal article describing the calculations in this regional subsetting and the application in the Journal of the American Water Resources Association. And if you Google that title, you'll see that. And if you have any questions about any of this, our email addresses are shown here. Would be happy to answer any questions. And in some cases, we have people send us shape files and we upload them. And it's really a simple process to use once it's implemented. And we're excited about the further potential for use of this in West Africa and other regions, severe hubs around the world. Thank you.